Hello, discrete math fans. Let's talk about truth values. Now remember, we talked about sentences and statements. In order for a sentence to be a statement, it must have a truth value associated with it. That is, it has to be either true or false. Now we're going to define some compound sentences. They're statements, and we're going to specify their truth values in terms of the truth of the statements that compose them. So when we talk about compound statements, that means we're creating new ones from old ones using our logical operators, like not, or, and. So first let's make some definitions about our logical operators. So let's make a definition. If P is a statement variable, then the negation of P, which we'll call not P, and is denoted with the squiggly P that we talked about before, it has the opposite truth value from P. That is, whenever P is true, then not P is false. If P is false, then not P is true. Now, we're going to display the truth values for this negation operator in what we'll call a truth table. This right here is the truth table for the negation. So it shows you the possible values of P and what the values of not P will be. All right, now let's make a definition about the disjunction. So the disjunction of P and Q, this is P or Q, and remember that we used this V symbol. It's true whenever P is true or Q is true, or even when both P and Q are both true. The only time it's false is when P and Q are both false. So let's show a truth table for the disjunction. So it looks like this. So we're showing all four different combinations of truth values of P and Q. And then P or Q, that's the new symbol that we're creating, will be true whenever either one of them is true, or both. And the only time it's false is if both P and Q are false. And finally, we have our conjunction. This is P and Q. The only time this is true is when both P and Q are true. If either of them is false or both are false, then P and Q is false. Just like before, we're going to show a truth table, this time for the conjunction. Looks like this. So the only time that P and Q is true is when both P is true and Q is true. We want to make a distinction between natural language and formal logic. Now in natural language, if somebody says to you, "Would you like tea or coffee?" that means you can have one or the other, but you can't have both. In mathematics, we're going to use the word or in a different way. In natural language, we use the exclusive or. When we use an or, one or the other must be true, but not both. However, in math, we generally use what's called an inclusive or. We're going to say that the statement form P or Q is true whenever P or Q are true, or both could be true. Okay, that's all for now.